Imagine trying to figure out what's happening, deep inside our planet, miles down.
Yeah, it's tough.
We're talking magma churning, fault grinding, these immense pressures building up. Predicting something like a massive earthquake or a volcano? Well, it often feels like an impossible task, doesn't it?
It really does. Our current tools have limits.
Exactly. Our relationship with the Earth has mostly been, well, watching, observing, or maybe just, holding on when things get rough.
Reactive mostly.
Right. But what if we could? What if we could flip that? Move beyond just observing these huge planetary forces and actually maybe engineer them.
That's the core idea. It sounds bold.
It sounds completely audacious, yeah.
Yeah.
Almost sci-fi. But that's exactly what we're going to dive into today. So consider this your shortcut to getting your head around a really paradigm-shifting concept about how we relate to Earth.
You framed it perfectly. The concept we're exploring is called Geosynthetic Programming, or GP. It's a vision put forward by Mr. Shahryar Ghiasi. And it's fundamentally about transforming the lithosphere, Earth's solid outer bit, from this sort of passive system we just react to.
Like waiting for the next quake.
Exactly. Into something that's actively monitored and, yes, engineered. It's a huge leap from just studying geology to actually potentially influencing it.
Okay. So for you, our listener, our mission today is pretty clear. We're going to unpack what geosynthetic programming actually is, how it might work, and what really profound, maybe even world-changing challenges it's aiming to tackle.
It gets pretty mind-bending.
I bet. So get ready, because this could really push the boundaries of what you thought was possible with our own planet. All right, so let's start with maybe the why. Why even think about something this radical? Let's look at geology as it is now. It's achieved amazing things, of course, but it is largely observational, right? Looking back at processes.
That's right. And there are some very real inherent constraints that limit what we can currently do. These constraints are really the motivation for considering a new approach like GP.
Okay, like what are the big ones?
Well, the first, and maybe the most obvious, is just inaccessibility. I mean, think about deep Earth processes, mantle convection, how faults actually slip deep down, or how fluids and rocks interact miles below the surface.
Things we can't just go and look at.
Exactly. We can't observe them directly. We rely on indirect measurements, seismic waves, modeling, which means there's always some interpretation, some guesswork involved.
And if you can't see it directly, I guess that makes predicting it super difficult.
Precisely. That inaccessibility leads straight to the next major hurdle, unpredictability. Our models for these incredibly complex, nonlinear systems, earthquakes, volcanic eruptions, they suffer from huge uncertainties.
Why is that? Just the complexity?
It's the complexity, yes, but also sparse data. We only have sensors on the surface or in relatively shallow boreholes. And even with massive computing power, there are limits. It's like trying to predict, the exact path of every single water molecule in a turbulent river.
Right. So that's why we still can't pinpoint the next big earthquake, despite all the research.
That's a big part of it, yes. We talk probabilities, not certainties.
Okay, so inaccessibility, unpredictability. What else? You mentioned resources earlier.
Yes, that links to the problem of reactivity. Our current methods for finding and extracting resources, minerals, oil, gas, are often reactive. We find a deposit, we dig it up or drill it out.
Which can be pretty disruptive environmentally.
It can be, yes.
Yeah.
And it's inherently finite. We're taking what's already there. And then finally, there's our limited control over hazards. Mitigation is mostly reactive, building stronger buildings, evacuation plans, or it's based on those probabilistic forecasts we mentioned. We can say there's a chance of a flood or a landslide.
But we can't really stop the underlying geological process once it's in motion.
Very limited ability to do that, yes.
Yeah.
We're mostly managing the consequences.
Okay. So you put all that together. We can't easily see what's happening. Deep down, we struggle to predict major events, we reactively take resources, and we have little direct control over hazards. I can see why the source material calls this a fundamental paradigm shift.
Exactly. It's not just about needing slightly better sensors or faster computers, although those help. It suggests a need for a completely different way of interacting with the planet.
And that, presumably, is where geosynthetic programming comes into the picture. Okay, so the problem's clear. Now, the solution proposed. Geosynthetic programming. How does it actually propose to, well, turn the Earth into something we can actively manage? You mentioned this idea of a closed-loop sensing analysis actuation system embedded in the lithosphere. That sounds ambitious, doesn't even cover it.
It's extremely ambitious, no doubt, but the vision is built on 5 core technological pillars that are designed to work together.
5 pillars. Okay, let's break them down. What's the first one?
The first pillar involves engineered nanoscale agents. The paper calls them GeoBots.
GeoBots. Okay, tiny robots?
Essentially, yes, but incredibly sophisticated ones. Think autonomous, self-replicating nanoscale agents designed specifically for deployment deep underground.
Self-replicating. Wow. How would they even survive down there?
Well, they'd need to be made from incredibly tough, chemically inert stuff. The concept mentions nanocomposites, maybe diamondoid structures or specially doped ceramics. Materials engineered to handle the insane pressures, temperatures, and corrosive fluids miles down.
And what would they do?
They'd be packed with capabilities. Multimodal sensors detecting strain, stress, temperature, chemicals, seismic waves. Microactuators, like tiny piezoelectric elements or heat emitters, to make subtle changes locally.
Actuators. So they don't just sense, they can do things.
Exactly. And critically, this idea of limited self-replication. They could potentially use common elements found right there in the rock. Silicon, oxygen, iron, calcium, magnesium to build more themselves.
Hold on, they build themselves using the rocks around them.
That's the concept. It makes the system potentially scalable and sustainable in a way deploying billions of pre-made bots wouldn't be. They'd also need energy harvesting and ways to communicate, at least short range.
Okay, my mind's already slightly blown. So you have these tiny, self-building, sensing, acting robots. What happens when you have, like, trillions of them?
That brings us to pillar number 2, the GeoNet. These GeoBots wouldn't just be randomly dispersed. They'd autonomously deploy, replicate strategically, and self-organize into this vast distributed mesh network of sensors and actuators.
A network within the rock.
Precisely. Embedded within critical zones, think major fault lines, magma chambers beneath volcanoes, or layers known to host valuable resources. And it would need smart communication, like mesh networking or data muling, where bots physically carry data packets if direct transmission is blocked.
Data muling bots.
Right.
Okay, so you've got this immense live network sending back just unbelievable amounts of data. How on earth do you process all that? And who or what decides what actions the actuators should take?
Right, that's color number 3, physics-informed AI. The proposal calls it TerraMind.
TerraMind, a planetary brain.
Sort of, yeah. It's conceived as a hierarchical AI system designed specifically to handle that massive, real-time data flood from the GeoNet. But here's the key part. It's physics-informed.
Meaning?
Meaning its algorithms, its neural networks, are constrained by the fundamental laws of physics that govern geology, conservation of mass and energy, rock mechanics, thermodynamics, fluid flow. It's not just pattern matching. It has a built-in understanding of how the Earth system must behave.
So it can't just invent crazy predictions that violate physics.
Exactly. It ensures the analysis is physically plausible and hopefully safer. TerraMind would constantly update what's called a high-fidelity dynamic digital twin lithosphere, a DTL.
A digital twin of the Earth's crust.
Basically, yes.
Yeah.
A real-time, super high-resolution model of the Earth's interior, resolving processes from the tiny scale of mineral grains right up to regional tectonic stresses. It's like having a live, constantly updated blueprint of the planet's insides.
Okay, so TerraMind, using this digital twin, analyzes the GeoNet data, figures out what's happening, maybe predicts what's next, and decides an intervention is needed. How does it actually do something? How does it command the GeoBots?
That's the 4th pillar, precision energy actuation. TerraMind prescribes specific micro-interventions, and then the GeoNet, those actuators on the GeoBots, executes them.
Micro-interventions, like what? What can they actually do?
The concept includes things like focusing ultrasound or elastic waves to tweak stress locally, maybe encourage tiny slips on a fault, or using targeted electromagnetic fields to heat a specific area, maybe alter mineral properties, or even microchemical delivery GeoBots, releasing tiny amounts of catalysts or reactants to steer geochemical processes.
So nudging the system rather than hitting it with a hammer.
Precisely. Small, targeted actions based on incredibly detailed sensing and analysis.
Okay, wow. We've got the GeoBots, the GeoNet network they form, the TerraMind AI analyzing it all, and the precision actuation to make changes. How do these all connect? What makes it a system?
That's the crucial 5th pillar. The closed-loop paradigm. This is what ties it all together into a continuous cycle.
A loop.
Yes. Step 1. The GeoNet senses the state of the lithosphere. Step 2. TerraMind and the digital twin lithosphere analyze that data and predict how things might evolve. Step 3. Based on that analysis, TerraMind prescribes a specific micro-intervention. Step 4. The GeoNet actuates that intervention. And step 5, which is critical, the GeoNet validates the effect by sensing, again, feeding new data back into the loop.
Sense, analyze, predict, act, validate,
Yeah.
and repeat.
Constantly. This is the fundamental shift. It moves geology from being descriptive, or maybe predictive if we're lucky, to being potentially prescriptive and proactively controlled.
It really is like giving the planet a nervous system.
Right.
Constantly sensing, processing, responding.
Yeah, that's right.
Yeah, that's where it gets really interesting. So we've sketched out this incredibly sophisticated, almost alive-sounding system for Earth. The big question then is, what could it actually do for us? What are the major geological headaches it might solve?
Well, the potential applications are pretty profound, targeting some of our biggest challenges.
Yeah.
Let's start with hazard prediction and mitigation. That's a huge one.
Earthquakes? Volcanoes?
Exactly. For earthquakes, imagine TerraMind identifying really subtle precursors, tiny changes in stress or strain along a fault segment that we currently miss.
Okay.
GP could then prescribe, say, targeted energy pulses from the GeoNet's actuators to induce controlled distributed microseismicity, tiny, harmless slips that release the stress bit by bit.
So instead of one giant catastrophic quake,
You could potentially dissipate the energy through a series of imperceptible tremors, preventing the big one from building up.
that alone would be revolutionary. What about volcanoes?
Similar idea, real-time monitoring of the magma chamber pressure, gas content, temperature. If things look dangerous, interventions could include localized cooling pulses, perhaps, or inducing some crystallization to make the magma thicker, less explosive, or maybe even controlled microfracturing to gently vent pressure.
Managing an eruption before it happens.
That's the goal. And even for things like landslides, the GeoNet can monitor soil moisture, pore pressure, slope strain in real time. Actuation could involve targeted drainage, or maybe stimulating microbes to precipitate minerals that strengthen the soil, a process called MICP, right where it's needed.
It's shifting from just warning systems to actual prevention systems. That's incredible. What about resources? You mentioned we're reactive now. Does GP change that? Is it just like super efficient mining?
It's potentially much more than that. The vision is a move toward sustainable resource engineering, maybe even in situ synthesis, not just extraction.
Growing resources inside the Earth.
Sort of. For minerals, say lithium or rare earth elements, cobalt, things we desperately need for batteries and tech, TerraMind could identify the right geochemical conditions, the gradients. Then GeoBots could inject catalysts or precisely tweak temperature or pH to encourage those specific minerals to precipitate out of the groundwater within engineered reactor zones.
So you'd essentially concentrate the desired mineral in one place.
Exactly. Creating a sustainable, high-grade deposit that could then be accessed with much less disruption than traditional mining. Less digging, less waste rock, potentially a much longer-term supply.
That sounds like a game changer for resource scarcity and environmental impact. What about energy, like geothermal?
For geothermal, or even managing old oil and gas fields, the GeoNet could map the fluid pathways and reservoir properties in unbelievable detail. Actuation could then be used to optimize heat extraction or fluid recovery, manage pressure, and potentially extend the productive life of these resources significantly.
Okay, hazards, resources. What about broader environmental issues? Climate change is the elephant in the room. Could GP help with something like carbon sequestration?
Yes, enhanced carbon sequestration and environmental remediation is another major potential application. When we inject CO2 underground, GP could actively manage the plume by monitoring its spread in real time, checking the integrity of the caprock above it to prevent leaks, and maybe even accelerating the process where CO2 mineralizes, turns into solid carbonate rock. GeoBots could deliver catalysts or nutrients for microbes that speed this up.
Locking the carbon away safely and permanently.
That's the idea. And beyond CO2, think about cleaning up existing underground contamination plumes of heavy metals or radioactive waste. The GeoNet could track them precisely, and actuation could deliver targeted chemical treatments or stimulate bioremediation to neutralize them deep underground before they reach aquifers.
Wow, okay, so hazards, resources, environment, this is all huge engineering. Does it also help us just understand the Earth better? Pure science.
Absolutely. But that's a crucial, perhaps slightly less obvious benefit, fundamental geoscience discovery. GP basically turns the Earth itself into a laboratory.
An in situ lab.
Exactly. TerraMind could formulate hypotheses about deep Earth processes, things we currently can only theorize about, like mantle rheology or how minerals nucleate under pressure. Then It could instruct the GeoNet to induce very specific, controlled perturbations. A little heat pulse here, a slight stress change there.
And then watch what happens with the sensors.
Precisely. Observe the system's response with the incredible detail provided by the GeoNet. This allows us to test fundamental theories about planetary mechanics in a way that's completely impossible today. It could accelerate our basic understanding of how Earth works at a fundamental level.
This vision, geosynthetic programming, it's genuinely extraordinary, almost feels utopian in its potential. But let's bring it back down to Earth, so to speak. It sounds incredibly futuristic. What are the realities? I mean, what does it actually take to make this happen? There must be enormous technological hurdles.
Oh, absolutely. You're right to be skeptical. The challenges are immense and they're foundational. Let's just take the GeoBots themselves. We need to figure out mass production on an unimaginable scale. How do you even get them miles deep into rock? Deployment is a huge issue. Then, ensuring they're reliable long-term in those extreme environments, high pressure, high temperature, corrosive fluids, and that self-replication aspect.
Yeah, that sounds potentially scary. How do you control it?
Exactly. Replication control is critical. How do you prevent runaway replication? Safety is paramount there. That alone is a massive research area.
Okay, so the bots themselves are a huge challenge. What about the network, the GeoNet?
For the GeoNet, sending signals, whether electromagnetic or acoustic, through miles of heterogeneous rock is incredibly difficult. Signals get scattered, absorbed, ensuring the network can self-organize, maintain communication, reroute data effectively in that complex dynamic environment. That's tough.
And power, how do they keep themselves powered for decades? Energy harvesting needs major breakthroughs.
And the brain? TerraMind. AI is advancing fast, but this sounds next level.
Yep.
It is. For TerraMind, integrating data across such vastly different scales, from microseconds and millimeters up to years and hundreds of kilometers, is a major computational challenge. Ensuring the AI is safe, controllable, and robust is critical, especially when it's making decisions about intervening in the Earth. And dealing with the inherent ambiguity often, different geological models can fit the same limited data. How does the AI handle that non-uniqueness responsibly?
And finally, the doing part, the actuation.
Yes, actuation.
Yeah.
How do you deliver enough energy, precisely targeted deep underground, without needing, massive surface installations? Can we generate focused ultrasound or EM fields effectively at depth? And crucially, understanding how the complex Earth system will actually respond. Rocks and fluids don't always behave linearly. Small nudges could have unexpected larger effects. We need much better predictive models of those nonlinear responses.
So yeah, huge challenges across the board. It's clearly not something we'll see fully realized next year or probably even next decade. What does a realistic path forward look like?
It would almost certainly have to be phased deployment, incrementally. You'd start shallower in areas that are better understood and maybe offer high value or high risk, like well-monitored fault zones near cities or existing geothermal fields.
Start simpler.
Exactly.
Yeah.
Maybe with just sensors first, non-replicating ones, then add limited, carefully controlled actuation capabilities. And over decades, as the technology matures, as we gain experience and confidence, you'd progressively increase the depth, the autonomy, the complexity, moving slowly towards that full GP vision. It's a long-term research and engineering marathon, not a sprint.
Makes sense. And alongside the tech development, with this kind of potential power over planetary systems comes, well, immense responsibility. The ethical questions must be absolutely critical. How do we make sure we don't screw things up on a massive scale?
They are paramount. These considerations have to be baked in from the very beginning. First, the risk of unintended consequences. It's huge.
Like triggering a bigger earthquake while trying to prevent one?
That's the nightmare scenario, yes. Or maybe disrupting deep microbial ecosystems we don't even fully understand yet. Micro-interventions, even if precisely targeted, could cascade in unexpected ways. So, rigorous modeling before any intervention, plus very small-scale, carefully monitored pilot projects would be absolutely essential. You have to test the waters very, very carefully.
And the AI itself, TerraMind, having an AI potentially making decisions about planetary scale interventions that need serious guardrails, right?
Absolutely. That falls under AI control and safety. You'd need robust, human-in-the-loop oversight. Humans must be able to review, approve, or veto significant interventions.
So not just letting the AI run the show.
Definitely not. Certainly not initially, perhaps never fully. You need built-in fail-safes, transparent decision-making. We need to understand why TerraMind is recommending something. And internationally, we'd need agreements, treaties defining what kinds of interventions are permissible and under what strict conditions.
And who gets to benefit? If this technology makes resource extraction super efficient or controls hazards in one country, what about others?
That's the critical issue of equity and access. The potential benefits, safer communities, sustainable resources must be shared globally. We need mechanisms to prevent this becoming a technology only wealthy nations can afford or control, potentially creating new geopolitical divides over resources of safety. Ensuring equitable access is vital.
It sounds like we need a whole new level of global cooperation.
We absolutely would. Which leads to the final point, planetary scale governance. The scope of GP is potentially global. You'd likely need a new international regulatory body at our mine. The source suggests something like a lithosphere stewardship council.
A what?
A lithosphere stewardship council. An international group to oversee the research, the deployment, the operations. Its job would be to strike that incredibly difficult balance, enabling scientific progress and hazard reduction while ensuring resource equity and environmental protection for everyone. That's a massive governance challenge on top of the technical ones. Hashtag tag tag outro.
Wow, what a deep dive that was. Geosynthetic programming. It really presents just a monumental scale of ambition, doesn't it? It's talking about shifting from us just being, passengers on this planet.
Often just reacting to what it throws at us.
Right, to potentially becoming its engineers,
Hmm.
actively managing and maybe even shaping its future stability and productivity.
It truly is a fundamental paradigm shift for geology and our relationship with the Earth. Moving beyond just reading the history written in the rocks to perhaps carefully, thoughtfully helping to write the next chapter. The potential rewards you mentioned, reducing hazards, sustainable resources, climate mitigation, deeper understanding, they are immense.
It's ambitious, as you say, maybe increasingly plausible in the very long term, but comes with those huge challenges and responsibilities we discussed.
Exactly. It's a future that requires not just technological genius, but incredible wisdom and foresight.
So a final thought for you, our listener, to maybe chew on. What stands out to you about this idea? Consider that immense responsibility that would come with having the ability, even in a limited way, to program our planet. How might a future like that fundamentally redefine what it means to be human living on Earth?